Okay. So, starting out with 13, 14. We did spend some time on 14 on Friday, so I will go over 13. I guess I'll just ask for specific questions on 14 rather than reviewing the same material, but we can get to that. So chapter 13, alkynes. Okay, what is the functional group of an alkyne? Carbon-carbon triple bond. Okay. A lot of this material is very similar to chapter 12, so I'm going to go over it now, but just remember that it really does transfer. When you're talking about alkenes and alkynes, there are a lot of similarities. The only difference is you have an extra pi bond in an alkyne, so just keep that in mind as I'm going through this beginning part. So it's really important to understand the difference between saturated and unsaturated. What does it mean to be unsaturated?
There's double bonds, so more addition reaction can happen.
Sure, so a double or a triple bond, okay? So unsaturated just means you don't have as many hydrogens as you could have. That's the best way to describe it. So saturated, we're talking about alkanes. Unsaturated, if you add a double bond or a triple bond, you have to remove some hydrogens to add those bonds, okay? So you're no longer saturated with hydrogens. So alkynes are considered unsaturated. Some terms to understand: terminal versus internal, okay? So, you know, trust your instinct on this. If we have, you know, an alkyne group at the end, that's considered terminal, okay? If the alkyne is in the middle of the molecule, that's internal. Which one is considered more stable? Internal, okay? In terms of naming, for alkynes, you just add yne. For alkenes, ane. The important thing to remember is you have to locate where that bond or where that functional group is, okay? So if you have, I'm not going to write in the hydrogens, but who can name this one for me?
2 pentene.
Pentene, right?
Pentene,
yeah. So why not 3 pentene?
Because you're going to start from...
Right, so you want to number both sides exactly and always give the lowest number. Does everybody understand that? Okay, you've had like a couple structure quizzes, so we're not going to go too much in depth with that. Okay. So in chapter 1, you talk about pi bonds and sigma bonds. It does review this in this chapter again. When you think sigma bonds, think single bonds. Pi bonds are anything on top of that, so double or triple bonds. Okay, so if we're looking at this carbon-carbon bond, we always have one sigma, and then every bond on top of that is considered a pi bond. So we have 2 pi bonds here on top of the sigma bond. Is anybody confused by this? We're all good? Okay. And just remember, he could also ask you for the number of electrons. So he might say, how many pi electrons? Okay, so just remember to multiply this by 2. Which is relatively stronger, sigma or pi?
Sigma.
Sigma, very good. Okay. What is the orbital hybridization of this carbon?
SP.
SP, very good. Anybody confused on how you find orbital hybridization? You all feel okay with that? All right. Let's see here. When we're talking about hydrogens near an alkyne or even an alkene bond, okay, you have to remember that they're very acidic. So more so with an alkyne than an alkene, but anytime you have hydrogens near a double or a triple bond, they're going to fall off more readily. Okay, so that's the same for both. In chapter 12 it talks about that as well. see. You should also know a little bit about how these act in the NMR. So again, when we're talking about alkenes or alkynes, these tend to be de-shielded. So in Chapter 10, Dr. Cosper talks specifically about how electron withdrawing groups, okay, so things that are very electronegative, pull on the electrons from their surrounding nuclei and de-shield them. You can think of pi bonds in the same way. So anything that has a pi bond is going to be de-shielded. Do you have a question, Amber?
I thought for alkynes it was shifted upfield.
No.
Which one was that for? Because one of them was different.
I don't think so.
No?
I would.
All the same?
Yeah.
I'm so confused. Okay.
I'm not sure if maybe there was something. I don't know if maybe in his notes he mentions, you know, a specific
Yeah, I
functional
thought
group.
he said in class that alkynes were shifted upfield and that they were the only ones.
I was gonna say, does anybody else have? I mean, I'm reading from Dr. Cosper's notes. I don't look through Dr. Fred's notes each.
That's what I was looking at too.
Yeah.
Which one?
Because I have it in my notes that it shifted upfield, and that's from his class.
So I would double check that. In reviewing I did review the chapter for Chapter 10. I haven't reviewed in the book for Chapter 13. But essentially, the pi bonds in an alkene act the same way as the pi bonds in an alkyne. So it's going to pull on the surrounding, if there's carbon 13, it's going to pull on those, and those are going to show up downfield, and the hydrogens as well. Kelsey, have you reviewed the textbook? I know you tend to. No? Okay.
But that would make sense.
I would just double check maybe his notes, Amber.
Yeah.
If you do find something, please let me know and I'll make a correction, but there is a possibility. Typically, though, pi bonds and electron withdrawing groups, you should think de-shielded. So they're going to show up in the downfield, okay? All right. All right, the next piece, there's a lot on different reactions. Some of them repeat in Chapter 12, so I'll try to cover those in this one, and then we'll just talk about the ones in Chapter 12 that aren't in here. Okay, so again, you're going to see a lot of similarities between these and Chapter 12. The main difference is when you're talking about reacting or doing addition reactions with alkenes, you do the reaction once. With alkynes, because we have another pi bond, you're going to see that reaction just happen again. So things are just repeated, okay? So in hydrogenation, we're obviously adding hydrogen, okay? This is a type of addition reaction, so we're going to break a pi bond, add hydrogen, and then break the other pi bond, add more hydrogen. A simplified way of drawing this is you're adding two hydrogen molecules. When you break both those pi bonds, you're just left with a single carbon-carbon bond. And the hydrogens are going to be added here. So, hydrogenation, alkene plus hydrogen equals what?
Okay.
Okay, okay. That's really all you need to know. I do know that he sometimes has talked about catalysts, so for this one, you should know that there's Lindlar's catalyst, and then this one is specific for cis alkenes. I wouldn't go much deeper than that. So hydrogenation, Alkyne plus hydrogen equals alkane. And this is very similar to hydrogenation with alkenes. Don't worry about the catalysts for that one, but with this one it's just one less hydrogen molecule. On the next page, Dr. Cosper talks about electrophilic addition versus radical addition. This is some, oh, sorry.
For the Lindlar?
Lindlar, yeah.
Is it, you said alkynes or alkenes?
So this is, well, when you're making cis alkenes.
Alkenes.
Yeah. So essentially it's kind of after the first step. If you use this catalyst, you'll end up with a cis alkene,
Okay.
and then it will continue on to making an alkane.
Okay.
Good question. So electrophilic versus radical addition. This is something that I talked about when we reviewed chapter 12. You can, and I would recommend remembering these terms and how they relate to the Markovnikov anti-Markovnikov rule. Okay. So anytime you see electrophilic addition, that's going to give you, it's going to run Markovnikov. Anytime you see radical, it's going to be anti-Markovnikov. This just relates to where the hydrogen is going to be added. Okay? Do you guys want to review Markovnikov versus anti-Markovnikov? I see a couple of yeses. What's up?
On Cosper's notes for chapter 13,
Mm-hmm.
so it says electrophilic addition of HX or
Yes.
hydron, whatever.
Yep.
And it says radical addition of HBr or yeah. So let me see. That radical addition doesn't look like it's going to be the same as that one, I think.
Right. So that has to do with the rule that it's following. So
Okay.
with electrophilic addition, it's going to run Markovnikov, which means that the H is going to the less substituted carbon.
Mm-hmm.
Whereas this one, the H goes to the most substituted carbon.
Yeah.
You see that on her notes?
I was just asking, do you think radical addition of HBr will be on his final?
So I don't know if he's going to use hydrobromic acid, but he could use any HX.
Okay.
So that the X just refers to any halogen. So I wouldn't necessarily memorize bromine.
Okay.
But I would know the general rule that it follows. Okay? So with radical, the H goes to the less substituted. So I would know electrophilic Markovnikov. These really lend themselves to fill-in-the-blank questions. Yes, Kelsey? Oh, sorry, more substituted. Thank you. So he could, describe electrophilic addition and ask you what rule this follows, or ask you where the hydrogen will be added. Or he could draw out the molecule and have you point to. So you just need to be able to identify most versus least substituted. We can go over this a little bit more when we go over chapter 12 because it comes up again. I think those are the big pieces of that part. There is the Heck reaction, which is probably the last thing I'm going to cover, unless you guys have specific questions. Okay, so the Heck reaction. Essentially you have an alkenal halide. All that means is you have a carbon-carbon double bond and a halogen, and you're reacting it with an alkene. Your final product has two carbon-carbon double bonds, What's the vocab term for a molecule that has 2 carbon-carbon double bonds? Diene. Okay, definitely important that you guys remember that term. Ene referring to alkene, and di obviously referring to di. The other piece we'll talk about in chapter 14. Those I would say are the big topics from this chapter. There definitely are other things that I didn't necessarily go over. We're just reviewing chapter 13 right now. Any specific questions from chapter 13? Amber, did I cover the topics that you were concerned about?
So for like the industrial FI,
Yeah.
so do we have to remember both of those processes?
I wouldn't worry as much about the first one, oldest large-scale production of ethine. I would know that one just because he does sometimes talk about them. I wouldn't worry about knowing the molecular formulas. So this ends up going on to make ethine, but I would know that these are involved in that process.
Okay.
As a fill-in-the-blank question, okay?
Okay.
I wouldn't worry about the, molecular formula of what lime is. I don't think that's going to be of concern.
Okay.
The other 2 industrial uses, I would know the names. So vinyl chloride, and then tetrahydrofuran, THF, knowing that that's the plumber's friend. Those are just popular questions he likes to sometimes put as fill-in-the-blank questions.
Okay.
Not necessarily relating to the mechanism of the reaction, but just knowing that it's involved. Those.
Okay.
Anything else? Move on to chapter 14. So we did spend quite a bit of time on chapter 14 on Friday. I apologize, it did take me a little while to get the video up, but it is up there now. I'll probably focus on just the concept of this chapter and talk a little bit about SN1 and SN2 reaction, because that's really the only thing we didn't cover on Friday. But I'll answer other questions, obviously. So this chapter is all on delocalized pi systems. And you also hear a lot about electron delocalization. And these really have, they sound scarier than they actually are, okay? So electron delocalization, all that means is electron movement. So the electrons aren't fixed in their bonds. And this occurs when we have delocalized pi systems, which you can essentially think of as alternating double and single bonds. When you have this is what they're referring to when they're saying delocalized pi system. Essentially, you have p orbitals that are lined up very nicely and allow electrons to kind of run through them. So the double bond, if we were looking, we're comparing this to this, okay? The double bond isn't stationary, okay? The electrons from this bond are also here and are also here. This creates a lot of stability, which is why it's talked about a lot in this chapter, okay? These molecules are unusually stable, okay? When you have like something I've drawn here, So a double, single, and then another double. That's referred to as a conjugated diene, which again is very important because of its stability. So you should definitely link this term with these terms, okay? So because we have pi systems that are nicely lined up, the electrons can move through them, creating stability, also known as resonance. So all of these words should kind of be linked up in your head, okay? This is all just one big concept. The only other thing we didn't really talk about on Friday is how these systems undergo SN1 and SN2 reactions. So I'm going to go over one chart in Dr. Cosper's notes. It's 14-3 if you're following along. So let's see. Okay, so these first three are really referring to chapter 6 and 7. Okay, so we have varying classifications of alkyl halides. Okay, so this would be a primary alkyl halide, secondary, and tertiary. Okay, now which one of these would react the fastest in an SN1 reaction?
Tertiary.
Tertiary. Why? What is created in an SN1 reaction?
Alkynes.
Carbocation.
That's a final product, but what's the intermediate is a carbocation. And we know that the most stable carbocation is a tertiary carbocation. So to get the most stable intermediate, we need the most stable alkyl halide. So this reacts very fast in an SN1, but it doesn't react in an SN2 reaction. Why don't tertiary alkyl halides react in an SN2 reaction?
Steric hindrance.
Steric hindrance, okay? Too many big methyl groups. Steric hindrance slows everything down. A secondary will react in both of these, but it'll be very slow. If we're looking at primary, we know that primary has less alkyl groups attached, so less steric hindrance. So it's going to react very quickly in an SN2 reaction. But it's not going to react at all in an SN1 because it makes a very unstable carbocation. Okay? That's just chapter 6 and 7. Okay? Alkenal halides, right? We talked about that a little bit. They don't react in either of these. This is talked about in chapter 13, but I kind of skipped over it. So no reaction in either of these mechanisms. Whereas when we're talking about a delocalized pi system, so just one double and one single bond, that's referred to as an allelic group. So an allelic halide is going to react quickly in both of these. So the first three columns are review from 6 and 7. This is coming from chapter 13. This is coming from this chapter. So you should be able to, he could ask you a question about SN1 mechanisms for any of these molecules, and you should know whether it's going to react quickly, react slowly, or not react at all. Any other questions from chapter 14? I'm only going over briefly just because we did cover a lot of this on Friday. If you guys have specific questions that maybe I didn't cover on Friday.
For the conjugated versus non-conjugated dienes,
Yes.
what's the difference?
So how many single bonds are between the double bonds and conjugated?
1.
1. What about non-conjugated? What does it show in the picture? I don't know if you have your picture up.
2.
2. So isolated or non-conjugated is just when you have more than one single bond in between them. So it could be 2, could be 4.
Okay.
Okay, that's the only difference. That's a good question. Anything else from chapter 14?